So this talk, the title of this talk suggests it's about particular method, and that's sort of true, but mostly this talk is about asking different questions that I think are interesting. So I'm thinking of a simple mixtures problem. So say we have two correlated ambient exposures and one outcome, and we'd like to know how the exposures relate to the outcome. And this is how we think they're related. So we've got beryllium and arsenic. I think they're probably related to birth weight, but they're also correlated, and we think that correlation comes through maybe some common source. I think this plot might look familiar to a lot of you. We have beryllium on the y-axis, arsenic on the x-axis, and these two are very highly correlated. These are actual data from results that I'm going to present. And this is sort of a common source of stress in any mixtures problem, is that we've got two highly correlated things, which essentially means that we don't have a lot of information to distinguish between these two exposures in fitting any sort of statistical model. Most approaches that we could use to learn about arsenic, beryllium, and birth weight involve something like a linear model. Or you could think of this as a logistic model if we were looking at, say, low birth weight. But the basic unit of analysis here is generally something like a linear model. Most applications involve directly interpreting beta 1 and beta 2. So the expected loss in birth weight per 10 nanograms per meter cubed increase in beryllium holding arsenic fixed. This is sort of statistics 101 or linear models 101. The problem is, though, that interpreting beta 1 and beta 2 directly can be problematic and lead to our inference being driven by the model rather than the data. So I'll get into why. So if you think about what the interpretation is of beta 1 in this model, again, it's an increase in arsenic holding beryllium constant. So if you look at just the plot, we would be comparing birth weight at the two extremes of this little whisker. On the left, we would look at the mean birth weight, and on the right, we would look at the mean birth weight, and then our comparison would be between those two groups. And that's essentially what the regression line is. It's thinking about sort of an intervention along this horizontal axis with arsenic. Problem is, this is also beta 1. So now we're in a region that's completely unsupported by data, but because we're using a model to smooth over the data, we're making inference in a lot of areas where we don't actually have any information. And this is part of the problem with mixtures, is that we end up with things that are so highly correlated that the models we fit just are not identified. So one other way to think about this, and the way that I like to think about this, is considering joint effects. Now, joint effects would be something like decreasing beryllium and arsenic at the same time and seeing what happens if you were thinking about doing this in a lab setting. But I like to think of joint effects as sort of intervening along the diagonal axis, where we're just decreasing all exposures at the same time. And at least the way I've drawn it here, this is well identified by the data. It's everything along that diagonal axis is supported by the data we've actually collected. So simply interpreting beta 1 and beta 2 may not reflect information among the exposures as well as joint effects. But which joint effect? And in order to answer that question, we should consider why exposures are correlated in the first place. So going back to the beryllium and arsenic example, one reason why they might be correlated is that both of these come out of the smokestacks of coal-fired power plants. And so one possible joint effect we could be thinking about is what would be the reduction in beryllium and arsenic if we could do something like decommission the coal-fired power plant. And this is why I say this talk is mostly about asking different questions. What I'm interested in is asking public health questions. I'm not a toxicologist, I'm an epidemiologist, so I like to think about what we might actually feasibly do in the real world. One thing we can't feasibly do is take a vacuum and remove arsenic out of the air. So joint effects really relate a lot to public health questions in the setting of exposure mixtures. Estimating effects of interventions on exposure sources integrates effects of multiple exposures, and it provides clear guidance for public health actions. The method for this talk is the Bayesian GFormula, and this is just a straightforward combination of Bayesian statistical models, so it could be a Bayesian linear model, and a causal inference framework that can be used to estimate effects of hypothetical interventions. It's a very basic algorithm. You could fit your favorite Bayesian statistical model. If it's not Bayesian, then this is just the G-formula. But a lot of times when we're working in mixtures, we run into problems where Bayesian methods can help because they provide some prior information. Step 2 is just to make predictions from that model that characterize interesting and identifiable interventions. And then step 3 is just to contrast those predictions. This is very straightforward in a Bayesian framework. And even in a frequentist framework, it's fairly straightforward. So the example that I'll be showing from actual data is estimating the effect of birth weight on reducing metallic hazardous air pollutants via a hypothetical intervention to decommission 3 coal-fired power plants in Milwaukee County, Wisconsin. So the exposure data from this come from the national scale air toxics assessment from 2011. And NADA contains both emissions data and then estimates of ambient exposure data on the census tract level. And we're focusing on 6 metals in particular, mercury, selenium, beryllium, arsenic, chromium, and nickel. And all of these metals had greater than 70% of local emissions from coal. And there was consistency between the NADA 2005 and NADA 2011. So this gives us 2 features. One is that if we actually could decommission the coal-fired power plants in the area, it would have a huge impact on each of these metals. And the other thing is that we know that these are consistent over time in terms of emissions. So given that we only have data in 1 year, we could expect, though, that if we decommission the coal-fired power plants, we would have a consistent lowering effect on each of these metals. So looking at a hypothetical intervention to reduce ambient exposure by the proportion of total emissions from the local coal-fired power plants. So the intervention we have in mind is what would happen if we turned off the power plant. We can't actually do that, and so the way that we operationalize that is just by decreasing, or thinking about decreasing by the proportion of emissions from the coal-fired power plant, each of these 6 metals. So, for example, nickel, 73% of the local emissions came from coal-fired power plants, and so the proposed intervention there is to decrease nickel by 73%. And the hope is that this emulates decommissioning of the local coal-fired power plants. So this is a map of Milwaukee County. The 3 dots in red are the 3 coal-fired power plants. You can see one is right smack dab in the middle of Milwaukee. And the sliding scale of color is beryllium concentration. And again, these are NADA data, so this is annual mean exposure for the census tract level. The birth data were drawn from about 27,000 births in Milwaukee City from 2010 to 2013 with complete birth record data on maternal race and ethnicity, smoking, marital status, age, child sex, and gestational age at birth. And because the Bayesian GFormula isn't necessarily a statistical method itself, I actually used it with 2 different statistical models. So one is just this very sort of vanilla flavored hierarchical Bayesian linear model with all first order interaction or product terms that include any continuous covariates. And so this is something that you might think is not well identified. And so we may be unbiased in the end, but this is going to be a very high variance thing. And this is a problem with mixtures, is that we end up with not being able to say much statistically about our exposures because we have such large confidence intervals and variances. The second statistical approach I compare is using the same model, but integrating Bayesian model averaging within this model. And all this does is average over all possible sets of terms, but then it includes a penalty for overfit. And so you can think of this as sort of a legitimate model that you might use in mixtures purely statistically. And both of these are integrated within the Bayesian GFormula framework. So the statistics of this are fine. If we want to interpret these as causal effects, we must make additional causal assumptions, and I won't belabor that because this is mostly about the method in the question. So now we're looking at results from this model, so we skip over a lot of the details of this statistical modeling. But what we see is that in Milwaukee, over this time period from 2010 to 2013, the observed mean birth weight was about 3,200 grams. which is a little below the national average of 3,400 grams. We can use the Bayesian GFormula to emulate no intervention at all, and this is just sort of a way to check that our model is working. And as you can see, under no intervention, or no hypothetical intervention, we see that we, again, retrieve the mean birth weight. Thinking about now what would happen if we decommission the coal-fired power plants, again, we compared two statistical models. The first one is just this sort of vanilla-flavored Bayesian hierarchical model that we think may be unbiased, but certainly is going to be high variance. And we sort of see that with the mean birth weight and then the mean difference in grams. So under this hypothesized intervention, we hypothesize that there would be, or we estimate that there would be an increase in the birth weight of 237 grams, which means if we shut off the power plant, we would actually improve birth outcomes. Using sort of a more legitimate mixtures model, which I think is what probably people are interested in, we see a smaller mean difference, but we have a much tighter confidence interval around that. So probably the best estimate from this, if you're Bayesian, is thinking if we turn off the coal-fired power plants, based on these metals at least, we suspect we would see a little bit of an increase, but it would certainly be statistically significant. And whether or not that's meaningful on the population level, hard to say, but certainly we would see an improvement in birth outcomes based on this intervention. So under the stated assumptions, to the best of our knowledge, we would have observed a 68-gram increase in the average birth weight up to 3,259 grams. Even if the causal assumptions don't hold approximately, the results estimate a standardized mean difference. So even if you don't want to believe that we've met all the causal assumptions, this is still a meaningful estimate. Just to give some quick acknowledgements, because we're short on time, co-authors on this project are Amy Kalkbrenner and Jesse Buckley. Collaborators include Karen Mikulski, other help from Ted Palma from the APA, who really sort of helped make sure that this wasn't too far out of bounds. And then funding came from a NIH NICHD grant. Thank you.